This module is triple integration in cylindrical coordinates. And really it's as much about introducing cylindrical coordinates as it is about doing triple integrals in those coordinates, but that's what we're going to do, and that's the application we're going to get towards. And we're going to end this module with an example of a center of mass calculation for an object volume that is amenable to cylindrical coordinates, as we'll see. So cylindrical coordinates are a step towards spherical coordinates, and cylindrical coordinates are generally, people find, pretty easy to understand because we've already talked about and used polar coordinates, and cylindrical coordinates are nothing more than that. You just add z variation to it and you have cylindrical. So when we think about cylindrical coordinates, we think about a point in space, and I draw it on the x, y, z axis, but it's just a point in general R3. And we're going to refer to that point as either an ordered set x, y, z in the plane, or r, theta, and z. So r and theta have the same definition as they have in polar coordinates. So if we just look at the xy plane, theta is the angle of the ray from the point from the origin to this point, which is the vertical intercept in the xy plane. So if r is the distance from the origin to this point, theta is the angle from the x-axis to r. So we have an angle, we have a distance r out, and then we have a height z now. And z is the same definition as it was in Cartesian. So z Cartesian, z cylindrical are the same. And then there's a relationship between x and y and r and theta, which is the same relationship we had for polar coordinates. It's instructive just to think for a second. We don't always say this, but what does it mean if these cylindrical coordinates are constant? If we said the surface at z equals constant. Well, z equals a constant is just a plane. It always has been. That's not new. So it's a plane above or below the xy axis. It's parallel to the xy axis at whatever height z is. So z equals 4 is a plane at z equals 4 over the entire xy plane. If theta is a constant, what does that mean? If we said the plane, well, the surface, theta equals pi over 6. Okay, well, pi over 6 is 30 degrees. What we'd be saying is it's a plane that has one edge along the z-axis and then comes out to infinite r at the angle pi over 6, in this case, from the x-axis. So it is also a plane. So z equals constant is a plane, theta is constant is a plane. What is r equals a constant? We've used this before. If we said the surface r equals 4, in the xy plane, if this was polar coordinates, that would be a circle of radius 4. But when we're talking about 3D and cylindrical coordinates, r equals 4 would be a cylinder of radius 4, parallel to the z-axis. Okay, all right, that's cool. To convert between, if you had r and theta and z and get to x, y, z, it's as before. R equals r cos theta, sorry, x equals r cos theta, y equals r sine theta, and z just stays as z. That's the same. This is just what polar was. And now we just add z. And then backwards, if you have x and y, so r squared equals x squared plus y squared, tan theta is y over x, and that's just obvious from this triangle here, right? So theta is the inverse tangent of y over x, and again, z is just z. And again, these are just what we had for polar, and z is the same. When we move to triple integration, then, we have to worry about two things. We have our integrand, which would be cast as a function of r theta z. If you had an integrand that was cast as a function of x and y, you would use x, y, z, you would use these equations to convert it to r theta and z. And then dv is just like for polar, you have r dr d theta and then dz. So it's just the polar area element, dA, which was r dr d theta. Now you add dz to the end. So a triple integral then would just be an iterated integral of some integrand, a function of cylindrical coordinates. You'd have r and then dr d theta z. Now here I've written one example of an order of the iteration, right? There are usually 6. Well, not usually, there are 6. Here I said, okay, I have some function of r and theta from one function to another, and then a function from another function is a theta limit, and then alpha beta. Now it's clear from this then, if these limits are r and theta, the first variable I must be integrating over is z. if then the next what I'm left with is a function of theta in the limits, I must be integrating over r, and then when I'm done, alpha beta must be angles. And that's why I wrote this as dz first, because that corresponds to this, dr next, because that must correspond to this, d theta at the end, that must correspond to this. Not super critical how you order these really, but keeping these limits as r and theta, then you have a constant, that always must be the case. But you could pick other orders just like we can for triple integration in Cartesian coordinates. Okay, and this, by the way, this whole thing is basically from the module entitled Triple Integration and Cylindrical Coordinates. I'm assuming you have this with you while you're listening to this, because we're going to do the same problem and we might skip some of the steps. We'll see how this goes. So let's do an example, triple integration in cylindrical coordinates. Relatively simple, but you know, it's got a little bit of work to it. We're going to do a center of mass calculation. So the problem would say we have a solid, and this is example 5 from section 915 of the textbook. It's also done in the note module. So a solid in the first octant with a shape determined by the graph of a cone z equals x squared plus y squared, and planes z equals 1, x equals 0, y equals 0. Okay? Find the center of mass if the density is some density of phi theta z equals k times rho. Now, this k part, I'm adding this coefficient k so that we actually have real units in this problem. And even in the note modules, I don't really do that. But the idea is the density is proportional to, oh, that's not rho, it should be r. R, okay? Rho is going to be the radial distance for spherical coordinates, so I was kind of mixing them up. Okay, so the density increases with distance away from the z-axis, because r is the distance away from the z-axis. It doesn't depend on theta, and it doesn't depend on z. I've got this crazy surface, so now we're going to integrate out and find the center of mass here. Now, remember, first thing I'm going to do is let's just draw this volume, and then we'll remind ourselves what center of mass calculation looks like. So I'm going to draw it up here, and I'll leave it up here. So we've got z, I've got n, I've got here, okay? And so we've got this cone, right? Right, which has a quarter circle shadow in the xy direction. So this is the cone. It's z equals square root x squared plus y squared, right? So when x equals 0, z equals y. When y equals 0, z equals x, right? It's limited by the y equals 0 plane, the x equals 0 plane, which is the first octant. Okay, so actually these two statements are redundant. And the important thing is this caps off at z equal 1. We have the vertical plane z equal 1 is topping this thing off. And this is the thing I want the center of mass for, but the density is going to increase with distance away from z. And actually it'll be 0 density at r equals 0, whatever that means, but increases out to k at r equal 1. So k must have units, by the way. This thing, if density has to have units, right, of kilogram per volume, so that must mean that k has units of kilogram m to the minus 4. Okay, so that's a coefficient. Together with r, the product of two would give us units of density as you would need. And when we get to the end of the problem, we can ask the question, are the units make sense? Which is a helpful thing to be able to do in real situations. Now, we have to remind ourselves what a center of mass calculation looks like. And if you remember from Physics 1401, so just in a one dimension, right? Let's say for x, the x center of mass for a discrete set of masses that are stretched out along the x-axis, the masses could be different, right? Was the sum of the individual masses times their x-coordinate divided by the sum of those individual masses, right? And we use that in first year physics and some to solve certain problems. We had a set of particles that were, say, acted on by no net external force, something like that. Now this thing, remember, no, it has units. This ends up having units of meters, right? Because we've got mass times distance along this particular axis divided by the total mass. So we need to have two integrals, one integral for this and one integral for this. So more generally, and the textbook goes this a bit, we would say that, for example, the x center of mass would be what we call MYZ divided by the total mass, where MYZ is defined as, so equals with a little triangle on top is my defined as, right? It's the triple integral over the region of just a minute. Yeah, okay, MYZ would be, well, the distance x times the density times the volume. So basically, density times volume element is a little mass. So this looks like x times m. So it looks like this. And we're summing it. So sum of the mass elements times the distance, sum of the mass elements times the distance. Yeah? And then the mass, right, is just the triple integral over the same volume of the density function and the volume function. Volume element. Okay? So when we do these center of mass calculations, there's two integrals we have to do. We have to do, well, in principle, there are four. There are three components of center of mass. We're just going to calculate one of them, frankly, right now. And you could do the other ones the same. So we'll calculate the center mass along the z direction. Okay, that's what we'll do. Now, but you'd have a mass integral, then you have three different ones of these. You have an integral for the x distance, the y distance, or the z distance, whatever we would want. Okay, now, so let's configure this. I'll leave that picture up there. Okay, so let's calculate mass first. Okay, so our mass is going to be, like I say, it's a triple integral of d. And we have our, remember our density function equals k times r. Okay, so we're going to have k times r dv. And now all we have to do is we have to get the limits of integration. This thing here is already, we were given this in cylindrical coordinates. We know the density is a function of r, so that's in cylindrical coordinates already. We don't have to convert anything. We just have to decide how we're going to integrate this thing. So it's an iterated integral. We have to decide the order. So we'll do the z integration first, because that's sort of a height of two defined height functions, and then we'll go. Then we'll decide whether to go r and theta. Remember, we're doing this in cylindrical. So if we do this here, theta goes from 0 to pi over 2, and r goes right from 0 to 1. Right? I know it's r equals 1 because we have a cap at z equal 1, and its endpoints here are 1 and 1, so that falls down. This is a radius of 1. Okay? And z, the bottom of z is the square root x squared plus y squared, and the top of z is 1. The bottom is the cone surface, the top is the top. So, this thing, I'll do theta on the outside. I'll do r next. I'll do z there. Then I have k times r, and then I have r d, I'm doing z, dr, d theta. Okay, so that looks good, except one thing. as I've written it right now, I've got a mix of variables here. This I can't use. This is Cartesian. Everything else is in. This is in cylindrical, this is in cylindrical, z equals fine, but I need to get this into cylindrical coordinates. And it's easier than it looks. I've got x and y, so I'm going to have to get r. So we know that r squared, remember that r squared equals x squared plus y squared. So this whole thing means that this integral is actually r. Right? This is a constant and can come out the front. So let's just go up here. So the mass equals, okay, I've got my coefficient out front. Then I've got, let's be a little careful in this next step. 2, 0, 1, and I've got r to 1, and I've got r squared dz, dr, d theta. Okay. Now, so there's no z variation here, so this whole thing just becomes, I'm going to do two things. I'll take the theta part out front, and I'll just say k pi over 2. We've seen this enough times. Since nothing depends on theta inside here, we can do the theta integral on its own first. Okay. We need the r case. And I've got r squared, because that comes out the z integral. And then I'm just integrating z. So now I've just got z from, sorry, this is, yeah, okay. Z from 1 to r, and then I've got dr. Okay, so this is k pi over 2, 0 to 1. I've got r squared 1 minus r dr. Okay, so this thing is k pi over 2, 0 to 1, r squared minus r cubed dr. So this is k pi over 2. Then we've got r to the 3 over 3 minus r to the 4 over 4, 1, 0. So this just becomes k pi over 2, 1 over 3 minus 1 over 4, right? Which would be pi over 24. Okay. Now, sorry, times k. Now, let's stop for a sec here. It's not easy, but to immediately, for a couple of reasons, to make sense of this in terms of units. Okay, so we've got k. So this whole thing should have units of kilograms. I've got k here, which we said had units. Let's remember that. So the units of k were kilogram meter to the minus 4. Okay. So I've got k here. Where's I should have somewhere meters to the 4th in here somewhere. So those cancel off, and I'm left with kilogram. Now, when we set the limits as things like 1, 0 to 1, pi over 2, we lose the obvious units, right? Because this 1 here is the height. This is units of meters. This has units of meters. Okay. So when we evaluate this, they bring meters in, and I've got r squared in here, which is meters squared. So actually, and there's another way to think of it. You can say this is meters squared, this is meters, this is meters. So that whole thing is meters to the 4th. Right? Now, if I had put a here and b here, then this would make sense at the end of what we'd have. Right? Right now, we sort of lose the units through here. But if we look back at the integral, yeah, indeed, this whole integral has the right units, because this is kilogram per meter to the 4th. This is meter squared, this is meter, so we end up with kilograms. So it does have the right units. Okay, that's our mass. So now we have to calculate the first moment. Okay. Now I'm going to calculate, we're going to calculate mxy. So this is the center of mass with respect to z axis. Okay. So really, it's the triple integral of z times rho times dv. So I'm asking what the center mass is along the z-axis. It's a separate calculation, do x and y, and we're not going to do that because it's the same thing over and over. So let's do this. So mxy, which is the first moment of the mass distribution with respect to the z-axis. That's what this is called. And first moment means you have a mass times a unit one distance, order one distance. The second moment would be mass times distance squared, and that will give us the moment of inertia. We'll do that later. So we have our triple, just rewriting this again, our triple integral of z times the density times dv. This is our density function. This is z. This is in cylindrical coordinates already. So we have, I'm still going to integrate in the same order we did before. So theta goes from 0 to pi over 2, r goes from 0 to 1. I have my z going from r to 1. We already talked about why that would be the case. Okay, what's different now is I've got k, r, z, and then dv is r, and then I've got z, dr, d theta. Okay, now I'll put these together, so I could call that r squared, so this is just going to be k. I'll do the theta integral, so we have pi over 2. Then I have my r integral here, and I'll leave my z integral, 1 to the r, and I have k out front, so I have r squared z dz dr. Okay. Now the r squared will come out, so I'm just integrating z, so this is k pi over 2, 0 to 1. And now we've got r squared came out, and then I've got z squared over 2 from 1 to r dr. Right? Okay, so I've got k pi over 2. Okay, we've got 1. I've got r squared, and then we've got 1 over 2 minus r squared over 2 dr. Okay, so we'll just simplify that out. Okay, pi over 2, 0 to 1, got 1/2 r squared minus 1/2 r to the 4th. I can bring the 1/2 out, so this becomes k pi over 4, okay? And then I have r cubed over 3 minus r to the 5th over 5, 1, 0. Just the 1/2 out. Okay. Yeah. So k pi over 4. Then we just have 1 over 3 minus 1 over 5. So that becomes k pi over 4, and then 15. So we got 5 minus 3 divided by 15. So that's 2 over 15. K, whatever, pi over 4, 2 over 15. So this becomes k pi over 30. Okay. So, okay. And similarly, when we think about units, right? K, let's go right here, K has units of kilogram meter to the minus 4. Then I've got meter squared, meter, so meter cubed, meter 4, meter 5. So m to the 5th, K kilogram per meter. So this whole thing has kilograms time meters. So it says units of kilograms meter, which it should, right? Because it's the numerator. So I divide that by the mass, I'll have units of meter, and that's what the units of the center of mass coordinate should be. So finally, the center of mass then, usually write that like that, Z with a hat on it, or a bar on it, right? Which is mxy divided by m is k pi over 30 divided by, what did I have before? K pi over 24. So k's cancel, pi's cancel. This is 24 over 30, right? Because it's k over 30 over 24. So that is 0.8, right? So makes sense. The center of mass in the z direction, first of all, is kind of up here, right? It's near the top, as it should be, because the cone's sneaking out, and there's much more mass out radially as we increase because the density is proportional to r. Okay, and you could do a similar calculation for the x and y axis center of masses. So that's example, non-trivial triple integration in cylindrical coordinates. If you look at previous year final exams, for example, sometimes I have problems where I say just set up the triple integral, say for this, for the first moment mass calculation versus the z-axis or something in cylindrical coordinates, and you would basically write this whole thing down. You sketch it, get the limits of integration correct, get the integrand correct, and do that. That's an example. Or you could do the whole problem, or we could ask various things like this. Okay, relatively easy. The problem coordinate system, or the problem geometry, I should say, will make it obvious whether this is you want to do this in cylindrical or some other coordinate system. Okay. So now, once we've done this case of cylindrical, we're just going to take the next step and move to spherical coordinates.